Good day, Dr. Hart.
Good morning. Oh, yay, I can hear y'all. Perfect. Morning.
I'm trying to get the classroom set up currently. For some
All right.
strange reason, nothing is doing what it used to do. So I'm trying to troubleshoot it and see what's happening. Because right now I don't
Hello?
know what's happening.
Yeah, gotcha. Okay, we've got a few minutes anyway. What was that? Schneider, was that you?
Yeah, Saif coming in late. I had trouble registering for your class.
Gotcha.
Jump through some loops to get here.
Gotcha. All good. Remember, Schneider, so this class is technically hybrid, but if you can be in person, I'd prefer you be in person. So think about that for next week, okay?
Jump in, try and get that done, you know.
Yep. Gotcha. All right. 3. Audio stuff. All right, big thing is make sure y'all are up in poll everywhere. Okay. Akeem, if you can help them out in St. Croix, make sure everyone's in because I know you know how to do it from last year. So if you're in poll everywhere.
Professor Rapp,
Yeah, what's up?
I have a quick question because I realized I missed that in my notes. So you remember the example where we were talking about the exam? When Alicia took the exam. It would be false when she gets an 80 and you don't give her $100, right?
Yeah, that's the
Okay.
only time that implication will be false.
Okay, thank you.
Yep. All right, were y'all able to get in? All right, Janai, if you or Brooks, sorry, you said you want to go by Brooks.
No worries. I mean, either or is fine. You're pronouncing it right, so that's okay.
Okay. So if y'all just want to like sit on opposite sides of the room and both have like, because I know Akeem's in here already, and you want to have your phone.
Yeah, I think I might just log in from my laptop and deal with this later. Okay.
Yep. So you should see, actually, let me just pull it up on here. People can respond. So right now, goal is to do poll everywhere. So we're gonna do our first daily quiz today. I know you gotta get set up for a second, Brooks. But if you look at Zoom, you should see either this or waiting for Aaron Rat 593's presentation. I wanted you, like I said out in that Blackboard announcement last night, to create an account so you can log in, create your account. And essentially what it's going to do is prevent you from having to type in your name every single time. It's just going to make it a little bit easier for you. And just in case you don't have it, let me throw it in the chat. Okay, so if you didn't, gotcha, Hakeem. All right, so if you didn't, go ahead, log in. You don't have to log in today. Make sure you create an account. Just type in your full name right here and then hit continue. So like for me, I would do Wrap. Continue, don't skip that. And then you'll see a page like this because I haven't started the quiz yet. So if I can get one, if you are not in 305, please turn your camera on. Remember, that was our condition. You can already see people wanting to default to black screens. Please turn your camera on. Okay. So I'm going to turn on or activate this quiz. Can I get a thumbs up if you see this page right here in Poll Everywhere, whether or not be in the browser or on the app on your phone. Cool.
Sorry, sir, but it looks like my webcam isn't really working right now.
Okay. Yeah, I see that issue. You can change the input. There's the little arrow beside the little video icon, little arrow or downwards facing carrot of V, and see if you can change your input. That might fix it. All right, so hoping Akeem, I didn't see if you gave me a thumbs up or not. I'm going to start the quiz. So you're going to see that page change. Right now. So you should now see this right here. Well, after I've logged in, so you have to log in. Forgot about that. So please make an account really quickly if you need to. I'll go ahead and log in because I already have an account. You can't see me typing in my password. Again. Join presentation. So you should see this quiz right here. Like I said, first day quiz. Just make sure we all get in, get to see this, get used to the logging in to Poll Everywhere, because I'm going to want y'all to do it before every class so we can make sure that these daily quizzes go smoothly and we can just get into the fun material stuff. But this is your daily quiz. What days of the week does our class meet? Should hopefully know this since we've now completed one full week. Okay. So I'm going to give you all just roughly one more minute. Hopefully get people in and get you to select your answer. Wonderful change, cool. You see I've got 4 responses. All right, Brooks, I see you back and in audio. Cool, cool, cool.
Yes, I'm back, Dr. Yes.
Cool, cool, cool. All right, so remember, cameras on, people, everyone. Cameras on, please. I've got 4 responses, and I see, what, 1, 2, 3, 4, 5, 6 people. Brooks, is there anyone else with you in 305? Oh, if you're answering, you're muted.
Yes, there's 3 of us in here. The same
Cool.
2. I'm not good with names, so I will learn names.
It's all good.
There.
So I just want to make sure the number of responses I'm looking for. So everyone should have, I've only got 4 responses to this quiz and Poll Everywhere. Everyone should have responded by now. I know, Brooks, you're getting your laptop up. So make sure.
Did you get my response, Dr.
Only people I've got responses from. Now I've
Can
got
you see
7
my-
responses. Cool.
Can you see?
I should be able to. Apparently, it's not one to do it
Oh.
on the iPad. Let's see. One, two, three, 4, 5, 6, 7. 3 go in there. Okay. So we're going to see. Settings, not there. Oh, I guess I got to go to reports. 1 second, y'all, because I do want to make sure everyone gets credit for being here today. If you have not responded, please speak up now. It's your last chance. And again, make sure that in the top right, it has responding as your name. Okay, responding as your name. That's how I'm going to make sure I keep track of who responded with what. If you don't have anything here, it's going to be like guessed something, something, something. I won't be able to know who guessed something, something, something is unless I get lucky. Okay. All right, so I'm going to lock answers here in 5, 3, 2, 1. So now you won't be able to change. You'll see it kind of gets faded away. And I'll go ahead and show y'all. Everyone got it right. Everyone who responded. Yes, it's Monday, Wednesday, Friday. Okay. So daily quizzes will always be at the beginning of class. Hopefully we won't have any issues getting 305 set up so we can get straight into them and not waste as much of our lecture time. I'll always make sure we go over the correct answer after these, and then I'll get your grades into Blackboard after class. Okay. So let me stop share there. Any questions? Real quick before we begin.
That was today's quiz? Like that was
Yep, that was today's quiz.
Oh, okay.
All right. So let me deactivate it. So now if you want to close that out, you can. That pull everywhere you can. All right, so we're going to get back into implications. That is one of the biggest things that we have in mathematics and in the real world. Get the note screen up. You exit full screen. Gallery, perfect. Okay. So implications. We're just taking two atomic statements. So again, just a statement that's either true or false. It can't be broken up into further statements. And we call that first one, the very beginning, what would follow an if, the hypothesis. We have what follows the then is the conclusion. You can also call them antecedent or consequent if you want to. Okay. Remember, this is the key thing here with implications, these statements. We are not at face value implying a relationship between the two things. Okay. We're not implying that there's a relationship between the two things. It's just if this is true, and then something about this statement, can we say whether or not the entire implication, the if-then statement we made was true? So that's what we were saying with this if-then, that last example we had in class on Wednesday, right? If Leah gets an 80 on the final exam, then I will give Leah $100. So essentially, a good way to think of it is that first statement, your hypothesis is your gatekeeper. Okay. If that is true, then I know I will give Leah $100. Okay. If it's false, then I don't ever get to go past the gate. I just surpass the entire statement. Okay. And surpassing that entire statement just means that I can't say it's false. Right? That's the thing. It was that backwards thinking. I can't say it's false. And if statements have to be either true or false, it can't be false, then the only option is that it has to be true. So if she doesn't get an 80 on the final, I'm not saying anything about whether or not Leah will get $100. I just know that this implication will still be true because I wasn't able to satisfy the hypothesis. Okay. And that's what we were going through. The only time that implication is false is if she did make an 80. So the hypothesis is true, but I did not give her $100. The conclusion is false, right? That's the only time that an implication will ever be false. So just to kind of recap the 5 different logical, I held up at 4, 5 different logical connectives that we have for our atomic statements. Let's just also sum up all that information, and a good way to do it is with a table, okay? If you ever kind of just Google discrete mathematics, one of the things that a lot of classes like to go through is just messing with truth tables because it gets you this way of separating logic statements from the statements themselves, right? We just want to talk about how they're connected together and then how the entire statement is true or false, depending on whether the atomic statements are true or false. And again, we don't care what the atomic statements are. So we're going to make this nice little table. Oops. I'm going to have just two statements. I'm going to start with P and Q. And again, there's 5 different ways that we can work with these statements P and Q. The first one was this right here. P something Q. Who remembers what that symbol represents? Go ahead and unmute yourselves.
And
Yeah, I think I saw you mouth that. I didn't hear it, Deanna, but and it might be audio on my end. Actually, real quick, can someone give me a test? Say something again, other than Deanna.
Yo,
I heard, okay, I heard it came, but it barely came through. That's on me. All right. I think I saw you say, Deanna, it's an and statement. So remember this right here. P and Q. That was one logical connective we had. Another one was this right here. Yeah. Or, yeah, I love that. A lot of people responded that time. Then the one that we were talking about here. P implies Q.
if P, then Q.
Mm-hmm. Perfect. If P, then Q. Then we also had this logical statement right here where we have the arrow pointing both ways. Anyone remember what that one was?
If and only if.
Yeah, perfect. If and only if. A biconditional statement. Oops, wrong pen. I'm writing really small, trying to fit it in there. And then the last one that we had, doesn't really matter which statement, whether I use P or Q. What does that symbol indicate?
Not.
Not, right? It's just the opposite. So if it was true, then not makes it false and vice versa. So what we can do is we can figure out just what all combinations of P and Q are, whether they're true or false, right? And then look at, again, what all of these different molecular statements using these logic connectives, what their truth value was. Essentially summing up all the information that we wrote down here, but just in a nice little table that we can always use to reference. Okay? If we ever forget how a logic statement works, we can come back and make sure we know the truth value. So we have the case where those statements will be true. We have a case where P will be true and Q will be false. We'll have the case where P is false and Q is true. And then what's the last one? Those statements are what?
Both are false.
Yeah, both are false. Okay. So that's the different combinations that we can have for P and Q. And then we have to remember, okay, well, the different connectives, when will that statement, in this case, P and Q, well, when would that be true? Well, we define it to be true only when both P and Q are true. So that first row, when both P and Q are true, that and statement will also be true. And everything else will be what?
False.
False, right? Because an and statement can only be true if both parts are true. And if I look at the other 3 rows, I see that at least one of those statements, P or Q, is false in all of those different rows. And so that's how this and statement works. It's kind of restrictive. Right? What about an or statement? Well, that's going to be a little different. Right? For an or statement, just one of them, one of the 2 atomic statements has to be true for the entire or statement to be true. So I see in that first line, both of them are true there, right? I have a P is true and a Q is true. So that or statement would also be true because at least one of them was true, right? Ended up being both, but at least one. Okay. That second line, well, P is true and Q is false. Well, will that or statement be true or false?
True.
Right? Yeah, I love this. A lot of people responding, not being afraid. Love this. Well, that third line is essentially the same thing, right? It just flipped which one's true and which one's false, but at least one of them is still true. So that or statement is going to be true. In that last case, both are false, which means my or statement's what?
False.
False. So if I'm connecting these two atomic statements together with an or, and both those atomic statements are false, the entire molecular statement with that or is also a false statement. Now we get into this P implies Q. And, well, if P is Q and true is Q, then P implies Q is also a true statement, right? If Leah made an 80 on the final and it was true, and I gave her $100 was true, then the implication, if Leah makes an 80 on the final, then I will give her $100. That is a true implication. That is a true statement. Again, I'm not talking about a relationship between the two atomic statements, just that the implication, the statement that I make of if she makes an 80 on the final, then I give her $100, that statement is true. What about that second line? So it's she makes an 80 on the final, but I don't give her $100. That would make the implication what? This is the only time. Yeah, this is the only time an implication is false, right? Where I essentially lied to you. You met the hypothesis, but the condition wasn't met. That is the only time an implication can ever be false. The other two cases are where my hypothesis is false, so I don't even satisfy the beginning part of my implication, which means I bypass it. And again, this is where we have to pull this logic. Well, if I bypass this statement altogether, it can't be a false statement. So it's the only other value that it can have. Well, it's got to be true. Okay. So that's how the 4 different cases for any implication that we have. Now, if and only if was a biconditional. So this if and only if statement will be true only when both are true or both are false. So I look at when, okay, both P and Q are true. Well, it's that very first line, which means if I try to join these together with an if and only if statement, then that entire biconditional will also be true. If one is true and one is false, this biconditional will be false. That's how we defined it. But if both are false, the entire statement is what? Both are false, the entire statement will be what? Oh, I saw Lance.
True?
Yeah, it'll be true. Perfect. Thank you for trying to wait. All right, it'll be true. Okay. So when we defined it, if you skimmed over your notes, these biconditionals, it's a way to make sure it's saying they're equivalent conditions. So essentially equivalent statements. So you're checking to see if both have the same value. So if both are true or both are false, that's the only time a biconditional will be true. And then the last one's relatively easy. You just flip the truth value, right? Well, I'm going to have repeated here. That first row, P is true, so not P is what? Well, not true or false. Well, again, I said P was true, so again, it's going to be false, and then it flips for the last two. True and true. So this is a nice way to just sum up all of that information that we defined on Wednesday. Okay. And again, one of the things we're going to study is that if and only if statement. Those are very, very powerful mathematics statements because you can show equivalence between kind of very odd objects, right?
Excuse me.
Yeah, what's up?
Can you explain the implied section again?
So that's how we defined it. I know you weren't here on Wednesday, so I'll get you to the that definition, and then kind of same thing with 153. Make sure you can get some notes from someone, okay? So implication is we're saying P implies Q, or not P implies Q. If P, then Q. We're not implying any relationship between. We said that type of molecular statement. So that combination is only going to be true whenever P is false or Q is true, or any combination of those two. The only time an implication will be false is when our hypothesis is, I have that mixed up there. It should be the other way, when P is true and Q is false. Because I'm lying. So you might want to fix that in your notes.
All right, can we stay on the screen for a bit longer? And write it down, just give me a second.
Yeah. So just write down that third one, because that's what we're going to be talking about a lot today. I can come back after class and show you this entire page, so we're not wasting everyone else's time.
All right. If you're coming back after class, then you can move on.
Cool, cool, cool. All right, so again, that reminder, I'm going to say it multiple times. The statement itself, okay, the implication that we're making, the if-then statement itself is false if it is false. So that entire if-then statement, if this is false, you are not, and I want to repeat, not saying that P does not imply Q. If this if-then statement is false, it doesn't mean there isn't a relationship between them. It just means you're not thinking of something, right? There's some outside variable that's affecting it, something you didn't think of. And you can always think of nuance. Nuance is what we love in mathematics. That's what's going to trip you up. Okay. All you're saying when that implication is false, P implies Q is false, all you're saying that P is true and Q is false. That's all you're saying. If you say an implication is false, all you're saying is the hypothesis was satisfied, the condition is not. Okay, so let's just go through some examples again, because this is a tricky thing to get away from, because when we're used to using if-then statements, especially think in a laboratory setting, right? If I do this to a Petri dish, then what will be the reaction? You're trying to prove something, which means you're trying to establish a relationship so that then the implication will be true. But you're not studying the implication, the statement itself, away from any relationships you're trying to establish. Okay, so it's a hard thing to sometimes separate. And I'll admit, what helps me out a lot is just going back to that table, right? Reminding me that this is just kind of, you're having to act like a computer, and these are the conditions that you're met, and this is when the condition will be true or false. The statement will be true or false. So, question is, are the following implications true or false? I'm going to write down 4 of them. We're just going to go through them. Actually, I'm going to write all of them down. Let's write all of them down first. Three, move that down a line. All right, there are 4 statements. I'll give you all a second to finish writing them down. But just to summarize it all or say it all. First one is just saying if 2 is equal to 2, then the sun is hot. That is the statement that we're making. Second one is if 0 is equal to 1, then 1 plus 1 is 2. Third one, if the 314th digit of pi is 4, then 0 minus 3 is equal to 3. And last one, if 4 is an odd number, then the 314th digit of pi is 5. Okay, so 4 different implications. So again, one of the things that we want to do, and we even saw it back in that truth table, is we want to break this down into the 2 atomic statements, the 2 statements that are making up this entire thing that's separated by the if-then, and those statements have to either have a true value or a false value. One of the things that we're also going to determine here is whether or not those atomic statements that we see here are true or false. Okay, so if we look at that very first one, we have 2 atomic statements here. Right, the first one is 2 equals 2. So you see if, and then should be, if we're writing this correctly, the atomic statement. So 2 is equal to 2. Then the second atomic statement, the sun is hot. Okay, so now we go look at the truth value of those 2 atomic statements. Is 2 equal to 2? Yes or no?
Yeah.
Yeah, right? Nice, easy, logical thing there. That's the point. I'm trying to make it obvious, right? 2 is equal to 2. That is true. That means here I'm having a true statement. And I'm trying to imply, well, is the sun hot? True or false?
Yeah.
True.
That's also true, right? So this entire implication is a true statement implies true statement, which means overall this if-then statement is what? True or false?
True.
True. True implies true is a true statement.
Excuse me.
Yep, what's up?
Where? So it's gonna mostly be word problems for this course, or only for like the first section?
No, this is just setting up examples.
Alright.
Most of this course will be proofs, which will be a little bit of essay writing.
Essay writing?
Yep, you can think of it that way. We're going to hopefully see a proof today, actually, before we leave class. Okay, but you've been doing proofs all along. We're just going to make sure you get a little bit of rigor behind it. Okay. All right, good question though, good question. So, second statement. If 0 is equal to 1, then 1 plus 1 is equal to 2. Again, I have 2 atomic statements here. What are the 2 atomic statements in this implication?
0
0
equals 1.
Mhm.
Yeah, Miss Hunt.
And then I think, yeah, both of y'all are probably gonna get that last one. Just trying to be polite and let the other one talk.
No, she got
Then
it, man.
one-
That's all you, Miss Hunt.
1 plus 1 is equal to 2.
Yeah, 1 plus 1 is equal to 2. Those are my 2 atomic statements, right? And I look at the truth value of these 2 atomic statements. What follows the if? I have 0 is equal to 1. Is that a true statement or a false statement?
False.
Yeah, false
Yeah, that's
statement.
false. Yeah. So this is a false. What about 1 plus 1 equals 2? True or false?
True.
True. Yeah. That means overall, this entire implication is a false implies true. So what does that mean for the entire implication? Is it true or is it false?
It's false.
True.
It's false.
True.
False.
False, right? This was that one condition. That one time that implications are false.
Got it.
Yep. Right? I lied to you, but I still follow through the conclusion. Right? I lied to you, still follow through with the conclusion. That's when an implication will be false. That's when I've lied to you overall. This entire if-then statement was a lie. Okay? Now, last 2 ones are the trickier ones. So I have if the 314th digit of pi is 4, then 0 minus 3 is 3. Again, I think both of you are probably getting used to spotting these atomic statements, so I'm going to go through it a little more quickly. I got the 2. First one is The 314th digit of pi is 4. The second one is going to be that 0 minus 3 is equal to 3. What do y'all think here? Well, again, look at the truth values here. This is true. What about you? What about this first one?
It's false.
It is. It will not. It's not actually. Should be true. If I checked it correctly, it should be true. So again, I get a true implies true. Actually, sorry. Should be false implies. Wait, what did I mess up? False implies true.
Isn't the second atomic statement false?
Yeah, the second part should be, well, false. It doesn't matter. That's what it was. It helps if you write down the statements exactly what you have in your lecture notes so you don't get confused. So I have here, it should be 0 minus 3. What is it actually? 0 minus 3 is actually what?
-3.
Negative 3. So, true implies false. What have I messed up? I feel like I've messed something up here, y'all. This would be false implies doesn't matter. This will always be a true statement. This is not the way I want to run this. I apologize. This is why it gets so confusing. This, but it's good. I wish I had my lecture notes. Let me go grab my lecture notes from, actually, no. I get to look at the book. It. So let's figure out where my mistake was. Here, we're going to share screen. I'm going to steal it from here. So great thing. This is why we love our textbook. I'll make this into a learning moment. I'll make my mistake into a learning moment for everyone, right? If you forget, where can you always go for reliable information?
The textbook.
Textbook. Yeah. Not the way I want to go about showing you this great piece of advice, but it's the way you go about doing it, right? If you ever forget, want to double check, this is where you go. So we're going to go find, we're going to talk about implications. Now, if my mouse would keep working, that would be awesome. So mathematical statements. Let's go connectives. So when P is false, Q is true, or both, which gives us when P is false, Q is true, or both. Either P is false, Q is true. Yeah, so it's true statement implies false statement, which means I had it right before. True implies false, and that's when it's P is true, Q is false. Which means P is true. All right, so that's what I'm getting mixed up on. So this entire implication is true. It's always going to be true. If you have your final, your conclusion is true, it doesn't matter. That was the key. And that's what I was supposed to dictate with this example. Let's get back to it.
So does that mean the second statement was true then?
So it would be true because you had a false implies true because you never met the condition. And that's what's screwing me up. So let's go back. It would be true. False implies true, which means I didn't even follow my own note. So let's recap because I know we had to take a little bit of mental gymnastics to follow me there. Okay. Again, this is not the way I loved. I'm going to make sure that nothing like this ever happens again. I apologize, but this is where it does get confusing. Okay. So again, we can focus on just this row of our truth table. And why truth tables are really nice. Really, implications are going to be true either when our conclusion is true. And in that case, when our conclusion is true, it doesn't matter what the hypothesis is. Okay? Doesn't matter what the hypothesis is. I also, if it's false, then the only time that implication will still be true as long as my hypothesis is false. Okay, so if both are false atomic statements and I combine them together with an if then. Again, it's if I lied to you. If you do meet the condition, if you do meet the hypothesis, but we don't follow through on the conclusion, that is when the if then statement is false. Okay, so keeping that in mind, let's go back and look at number 2. It was a false implication, or false hypothesis implies true conclusion, right? Well, it really doesn't matter if the hypothesis is correct or true or false because the conclusion is true, which means overall this statement should be a true statement, just like the NS said. Okay, and it matches up with that truth table, which I didn't match up with before. All right, so now we can look at that third statement and accurately figure out what it is. Okay, again, I have then the conclusion. Let's see, so it should be, I wanted to write something, so I'm going to change this one because I wanted to give you examples of all. Then so true and then false, 0 minus 3 is equal to 3. These were the 2 that I wanted to give you. Okay, so take a second, fix those. That third statement, I wanted it to be if the 314th digit of pi is 4, then 0 minus 3 is equal to -3. That'll be the third statement. Fourth statement, if 4 is an even number, then, then 0 minus 3 is equal to, in that case, I'm not having a typo. I am trying to say 0 minus 3 is equal to +3. And you'll probably see why here in a second. That last one is not a typo. In line 4, that is not a typo. All right, now we get back into it. We look at the truth values of the molecular or the atomic statements in number 3. So again, we have the 314th digit of pi is 4, and 0 minus 3 is equal to -3. Well, is 0 minus 3 equal to -3? Yes or no? True or false? Yeah, I see some people shaking their heads.
Yes.
Yeah, that is true. Does it matter whether or not that hypothesis, that first atomic statement, does it matter if it's true or false?
No.
No. It doesn't matter because if the condition is true, the conclusion is true, then the entire implication is going to be true. And that's the caveat that I wanted to show y'all, right? The kind of weird thing with these implication statements, if the conclusion is true, it doesn't really matter what you put in as your hypothesis. The entire if-then statement will be true, right? I could say, well, I don't want to say anything controversial, so I'm just going to leave it at that. I was going to try to pull up some crazy example off the top of my head, right? But I could say, you know, the water is warm. If the water is warm, then the number of people in this classroom number of students in the classroom I'm currently in is 0, right? Technically, you could say water is warm. I don't know how you define warm. I can't say whether it is or not, but there's no one else in this classroom with me. So the number of students in here is 0, so it doesn't matter what I put before it, that implication is still going to be true, right? That if then that I gave you is still going to be true. Now, what about that last one? if 4 is an even number, then 0 minus 3 is equal to 3. Again, 2 atomic statements. 4 is an even number. 0 minus 3 is equal to +3. That is the statement I made. Well, is 4 an even number? True or false?
True.
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 0 minus 3 is equal to 3. Is that true or false?
False.
Yeah, it's false. Right? It
Oh.
should be -3. Which means here, I now have a true statement implies a false statement. Overall, what does that mean for the implication? It is what?
The implication will be false.
Yeah, that one will be false. That is a false implication right there. And really the only time an implication will be false. When the hypothesis is met, but I lied to you about the conclusion. You know, the conclusion is false. Right? If we go back to that example from Wednesday, right? Leia did make an 80 on the final, but I didn't give her $100. That if then statement I made would then be a false statement. Okay. So questions so far. I know we had that little backtracking for a second, so I want to make sure that we're all feeling good. So if you're feeling good, yeah, Dana's got it. Give me a thumbs up.
Feeling good, Dr. Rat.
Cool, cool, cool. Want to make sure. Yeah, some of y'all even got the reactions going. Perfect. All right. So part of the reason why we spend so much time on implications is because implications are the backbone of mathematics. Pretty much any statement that you've seen in a mathematics textbook, any theorem is a if-then statement. Even definitions are technically if-then statements. If you satisfy this condition, it's then we call you something. Okay. So we not only want to make sure that we have the truth values, understand the truth values of implications that we're going to prove, but it also gives us ways to prove these implications later on. Okay, so implications. Of mathematics is definitely the backbone of mathematics and also other sciences, right? The scientific method is based on implications. I satisfy all these hypotheses. I want to show a conclusion. Granted, when we're doing this, especially in the world, we only care about one of those 4 cases that we have, right? It's when our hypothesis is true and we want to show that the conclusion is true, because that's usually our goal, is to show the conclusion is true. We want the conclusion to also be true. And that's why it's hard to separate from relations and implications, because that's what we naturally do. That's what we train to do as scientists in any field. Okay. So when proving implications, we always want the entire implication to be true. Okay, but are usually only interested in the case, oops, not writing, there we go. In the case where the conclusion is true. Right? Because we want to end up at what we're trying to show. We want to show the conclusion is true, which means then if I go back to my truth table and I want to have the conclusion true, that means that I also need the hypothesis to be true. And that's why we're stuck with when we're trying to relate these if-thens back to our normal experiences. We want them both to be true in those last 2 cases where hypothesis is false, the conclusion is true, or both are false. They kind of seem weird at first. So this is what is called proving or proofs. Okay, as a mathematician, this is what you do day in, day out once you get past your calculus. And even in your calculus and algebra courses, you're technically doing proofs, right? If I wanted to, well, not everyone has done this, but even back here, so if x plus 3 is equal to 12, then x would be equal to 9, right? This is an algebra, nice little simple algebra equation that you've done before, and you know how to prove this, right? I want to show that x has got to be equal to 9 from x plus 3 is equal to 12. So you would take that equation, x plus 3 is equal to 12, and then you would do what to both sides?
Subtract
And that's both sides by 3.
Yeah, subtract 3 from both sides. And then logically, because our rules of algebra say I can subtract the same value from both sides and the equation will still hold, we've now shown that, well, x has got to be equal to 9. Okay? So you've been doing proofs your entire mathematics career. Just one of the things we're going to do is going to say we're going to write it out a little bit more in depth. Okay? But we're not going to be sticking to just equations. We're also going to be sticking to properties of things. So to prove an implication, this is the key part right here, right? Since we're only really interested in the case where both the hypothesis and conclusion are true, so where we want our conclusion to be true, our goal is to show this conclusion. Is going to be enough to assume that P is true. So we can just go ahead and assume that our hypothesis is true and then deduce from this assumption. Or from this assumption, ooh, that second V is a little funky. Deduce that Q is true. Okay. Another way of saying, thinking of deduce, is to show that Q is true. So I'm already out of time. What we're going to do on Monday is work through our first proof. We're going to keep it pretty simple. Okay. I'm going to go ahead and write out the theorem, and theorems in mathematics are usually these if-then statements. They can also be those biconditional if and only if. But what we're going to prove is that if two numbers A and B are even, then their sum, that A plus B, is also equal. Okay, that's what we're going to prove. We're going to take this idea and we're going to try to train into ourselves. Okay, if I see an if-then statement, how do I go about proving it? Okay, in your biological sciences, what you do is you would start with your conditions, right? You still have your, you call it a hypothesis. Your entire if-then is your hypothesis, right? But you take your conditions and then show through your experimental procedure in your laboratory that your conclusion is going to come out in the end. Same thing we're doing here, right? Assuming P in this case is you having your equipment in the lab and setup ready, and then waiting a couple of days using your test tubes, whatever, right, is going to be what we're going to logic through with words and definitions. So I'll on Monday, I'll define what even numbers are, because that's going to be necessary. We need to have our tools, our mathematic tools, and then we're going to come prove this theorem. Okay. But remember, beginning of every class, we're going to have that daily quiz, so make sure you get poll everywhere up beforehand. And I'm going to let y'all go. I know Schneider, I'll move this screen up here in a second, but If you have questions, feel free to stick around and ask. Otherwise, you're good to leave. Hope you enjoy your weekend. Survived your first week.
You just say we can talk around.
Have a good weekend, everyone.
Yeah. Oh, Professor Rapp, just wanted to let you know that I'm getting my dose on Monday in the afternoon, so I would still be on Zoom. But
Okay.
on Wednesday, I could come in.
All right. No, thank you for telling me. All right, let me go up for Schneider. At least give you all of these. Give you a second. There might be another class that's trying to come in, so I might not be able to wait too long.
I'll be real quick. I'll
Okay.
just do some screenshots on that.
Gotcha.
Yeah, right? Got that page?
Cool. And then that was that example. So when you hear me talking about the whole, if Leia gets an 80 on the final, I'll give Leia 100. That's the example we were referring to.
All right, got it.
Cool. And then all that was left was just,
Yeah, I got that too.
cool. All right, that's essentially it. I don't think there's anything really important. Oh, I guess, yeah, you probably need atomic and molecular. That's in the textbook. It's a relatively easy concept to get. So if you go to the mathematical statement section of our textbook, which I had shared before, that's what I was scrolling through.
I get that one looked.
Yeah, so essentially just this part of the textbook right here. I can throw it in chat. So that was our textbook. And that's just the intro mathematical statements.
Okay. Hey, thanks for taking time of your day for this.
Yeah, my pleasure. Yeah, and I guess I can go and ask, do you have any questions real quick about 153? Well, I just got you here.
I think I'm all right.
All right, cool.
Yeah, have a good day, man.
You too.